A user opens your help center. They type one sentence. I forgot my login credentials. Your search runs. It returns nothing. Meanwhile, sitting in your documentation, there is an article titled, How Do I Reset My Password? That article is the answer. The search never found it. Look at those two sentences. They share almost no words. And yet any person reading them says instantly that these are the same question. So how does a computer decide that two pieces of text mean the same thing when it cannot read? The answer is simpler than you expect. Underneath, it is one idea from geometry. Start with what your database is actually doing. An exact match compares characters. A like query compares characters with wildcards. Even fuzzy matching, the kind that forgives typos, counts how many single character edits turn one string into another. All three measure the same thing, shape, the literal letters in order. Now feed them our pair. Reset my password, forgot my login credentials, edit one into the other, and you rewrite almost every character. To your database, these two strings are about as far apart as two English sentences can be. Now try the opposite trick. How do I reset my password? How do I reset my router? These two sentences are nearly identical. Change one word and you have the other. But one is about an account. The other is about a box on your shelf. They have nothing to do with each other, so you have two pairs. One pair looks different and means the same. The other looks the same and means something different. String similarity and meaning similarity are not the same measurement. You need a different ruler. Here's the move. You stop storing text as text. You store it as a position. Imagine a small space with two axes. The first axis measures how much something is about animals. The second measures how much something is about size. Take the word kitten. High on animals, low on size, it lands in one corner. Take the word elephant. Also high on animals, very high on size, it lands somewhere else entirely. Take the word skyscraper. Low on animals, very high on size. Now notice something. Kitten and elephant sit near each other along one axis and far apart along the other. Their positions already encode a relationship you never wrote down. Two numbers is a start. It is not enough. Two numbers cannot separate a refund policy from a shipping delay. So real embedding models do not use two axes. A common size is 768. Larger models use 1,536 or more. Every piece of text gets that many numbers. Here is the part that surprises people. Nobody labeled those axes. There is no dimension called animals. Nobody sat down and decided what each of the 768 slots should mean. If you open one up and look at a single number, it will tell you nothing. The model worked out its own axes. That sounds like a problem. It is not. You never need to read an axis. You only need to compare positions. You now have positions. Each piece of text is a point in a space with hundreds of dimensions. But do not think of them as points. Think of them as arrows. Draw an arrow from the center of the space out to each point. Every piece of text becomes an arrow, starting at the same origin, pointing off in its own direction. An arrow has two properties. It has a direction, which is where it points, and it has a length, which is how far it reaches. Those two properties carry very different kinds of information. Direction carries meaning. Length carries other things. How long the text is, how emphatic it is, how many times a theme repeats. Picture two arrows pointing in exactly the same direction, but one is 3 times longer than the other. The short one is the sentence, I forgot my login credentials. The long one is a full support article about resetting your password, 4 paragraphs long with numbered steps. Same direction, very different length, and they are about the same thing. Now measure the straight line distance between their tips. It is large. Distance says these are different. Distance is wrong. So ignore length. Measure the angle between the two arrows instead. That is the whole idea. Similarity is an angle. This measurement has a name you will meet everywhere. Cosine similarity. When someone says cosine similarity, they are asking one plain question. How aligned are these two arrows? Think of it as a dial with 3 landmarks. Arrows pointing the same way score at the top. Arrows at a right angle to each other score in the middle. which means unrelated. Arrows pointing in opposite directions score at the bottom. In practice, almost everything you compare lands somewhere between unrelated and closely aligned. A fair question at this point: who decided which direction each sentence points? Nobody did. The model was shown text, an enormous amount of text, more than any person could read in 1,000 lifetimes. And it was set a simple task: run over and over. Look at a piece of text. Guess what belongs near it. At the start, its guesses were random and its directions were random with them. Every time it guessed badly, its internal numbers were nudged, billions of times. Slowly, the space organized itself. Text that kept turning up in similar surroundings drifted into similar directions. This is why the words password and credentials end up pointing the same way. Not because anyone told the model they are synonyms, because across millions of documents, they showed up surrounded by the same neighbors. Login, account, forgot, reset, sign in. Meaning gets inferred from the company a word keeps, which leads somewhere uncomfortable. The model learned from human text, so it learned human patterns. All of them. Say certain jobs appear beside certain names, far more often in the training text. That lopsidedness shows up in the directions too. The space is a mirror of what it read. 3 things will bite you. Here's the first. Vectors from different models are not comparable, ever. Each model built its own axes during its own training. 2 models can both produce 768 numbers per sentence and still mean completely different things by them. Comparing across them gives you a score. The score is noise. So you cannot mix vectors from 2 models in one index. And when a better model comes out, you do not just swap the client library. You re-embed every document you have. Budget for that day before it arrives. The second one is stranger. Similar means similar in the way this particular model learned. That is not always the way you meant. Take these 2 reviews. The delivery was fast and the food was hot. The delivery was not fast and the food was not hot. To you, those are opposites. To many embedding models, they are near neighbors. Almost every word matches. The small word that flips the meaning barely moves the arrow. The same thing happens with sentiment. I love this product and I hate this product often sit close together. Both are strong opinions about the same product. The third one decides whether your whole system works. Chunking, how much text you hand the model at once. Embed a single clear sentence and you get a sharp direction. Now embed an entire documentation page covering billing and shipping and returns and account settings. You get one arrow that is an average of all of them. An average of 5 unrelated directions points nowhere in particular. It is weakly similar to every query and strongly similar to none. There is a storage cost too. Millions of documents, each carrying hundreds or thousands of numbers, adds up to a large index and a real bill. You have already met this idea in production, possibly without noticing. Semantic search is exactly the help center example. The query becomes an arrow. Every article is already an arrow. You return the closest ones by angle. Retrieval for a language model is the same step, with one addition. You take those closest chunks and paste them into the prompt before the model answers. That is the retrieval half of retrieval augmented generation. Recommendations work by pointing at items instead of text. People who read this also read that, turned into directions. Deduplication catches 2 support tickets worded differently that describe one bug. And clustering groups 10,000 tickets into themes nobody had to name in advance. They are one measurement, applied to different data. So hold on to one sentence. An embedding turns meaning into a direction, and similarity is the angle between 2 directions. Not shared keywords, not edit distance, not string length, an angle. Now go back to where we started. A user types the words, "I forgot my login credentials." Your keyword search compares characters, finds no overlap, and returns an empty page. Embed that sentence instead, and it points almost exactly where your article on resetting a password already points. The angle between them is small. The article comes back first. Same question, same content, a different ruler. One small thing before you go. Maybe the geometry made it click. Maybe you can now picture two arrows and an angle between them. If so, A-like helps this reach the next person who needs it. Subscribe if you want more explainers on the machinery inside AI systems, taken slowly and taken apart. And leave a comment with two things: which embedding model you are running in production, and what broke first when you shipped it. See you in the next one.